Welcome everyone to today's session. Today we have John van de Wetering for our first speaker. Dr. John van de Wetering is an assistant professor at the University of Amsterdam, specializing in quantum compilation and the ZX calculus. He is co-creator of PyZX, an open source optimizing quantum compiler, and his work focuses on quantum circuit optimization, classical simulation, verification, and diagrammatic methods for quantum computation. So I hope you guys enjoy his speech today, his talk today. We will be taking questions at the end, so please do not forget to put your questions in Discord, and I will ask them on your behalf at the end of his session. Following him, we have a lab tour, so please be sure to stay for that. So I'm going to now hand it over to Dr. John van de Wetering to share his information.
All right. Thank you very much for the nice introduction. Now let me set up my slides properly. Okay. I trust that you can all see that. Yeah, so I will be talking to you about some quantum software, in particular how to do circuit optimization using this thing called the ZX calculus. I'm going to explain what all those words mean. First, I'll just say, I'll start with a little advertisement. Like, if you like the stuff that I talk about here, and I guess in this summer school you've learned a bit about quantum computing already. We wrote this textbook, which is going to go into a lot more depth about like the things I talked about here, but like a lot more stuff than just that. And if you would like to continue on in doing quantum computing, we at the University of Amsterdam have this a pretty new master program called Quantum Computer Science. We have just started 2 years ago. We have our first couple of graduates now, so it's still pretty new. We have about 30 people starting this year, so you join like quite a small group of very enthusiastic people about quantum computing. Yeah, so also feel free to ask me like questions about this program if you want at the end. Okay, now let's get started with like the actual research talk here. So what do I mean with quantum software? So this can mean a couple of things, and like the thing that you might think of first is that this is actually the code that runs on a quantum device. So I trust that you've seen these types of diagrams before, these like quantum circuits that actually corresponds to instructions that run on your quantum device. But the thing I would like to talk about here in this talk is a different notion of quantum software, namely the sort of regular code, the regular software that makes your quantum code better. And so this comes in many different flavors. So we have optimization. So you give me some quantum code and then I run some classical procedure on it and then I make this code run faster. We can also talk about verification. So like, how do I verify that this code is actually doing the thing I wanted to do on my quantum device, or simulating it classically. So I can just see like, well, is this really giving me some quantum speed up, or is this something I can actually classically do as well? And then also a very important topic is error correction. So how do we run this without errors being introduced too much on my quantum computation? I won't be really talking about error correction in this talk, but I figured I would just mention it here. Yeah, so let's give a very brief rundown of quantum computing and how this works. So in the sort of standard quantum circuit model, we built our quantum computation from quantum gates. And these come in quite a few different flavors, but there are these single qubit gates, so they act on a single quantum bit. And here I have a picture of the block sphere and sort of the action of the block sphere, but you can kind of forget about this. And then we have a 2-qubit gate, the CNOT gate, which acts on 2 qubits at the same time. And then it turns out that these gates I've shown here, they're actually universal. So you can, if you want, you can decompose any quantum computation you would want to do into these gates. So in a sense, this is all you need. And now what these gates really are, they're just matrices. So they are a particular small matrices like this. But then, yeah, what you do if you have multiple qubits is you take these tensor products of these matrices, and then you get these exponentially large matrices. And nobody wants to deal with these things directly, because who wants to stare at like these really large matrices to see what it is actually computing? So people have devised a number of ways to deal with these things. And one of these things is this quantum circuit notation, where we introduce some shorthand for each of these gates, and we find a graphical way to represent them. So for instance, the X gate, or like what we also call the NOT gate, it becomes this little XOR symbol, or this plus symbol on a wire, where each wire will correspond to a qubit. And then the C-NOT gate, it's like exactly this like NOT symbol, and now there's a control wire attached to it. And then we also have a Hadamard gate, we have these Z phase rotations, and then these special Z phase rotations of Z, S, and T. And then we can just build arbitrary quantum circuit here, where we have our qubits sort of going vertically. So here we have 3 qubits and 3 different wires, and we have our time direction going horizontally. So we can kind of see like this directly tells us what operations in which order on which qubits do we have to execute these on a quantum device. And now if you want to run this, like I might give you some quantum circuit and I might want to ask you like, well, can you make this run faster? Can you do some operations to it to like use fewer operations? And like, the old-fashioned way you might do this is you stare at this quantum circuit and then you have a library of rewrites you can apply to it. So for instance, you might know that if I have two Hadamard gates here and they occur before a CNOT gate, I can actually push them through and the CNOT gate kind of flips direction if I do this. And then here I see I have two CNOT gates after one another, and CNOT gates are actually their own inverse, so I can actually cancel them. And now I have fewer gates in my circuit. So now this circuit hopefully runs a bit faster on my quantum device. I can compress it a little bit, and now I have a smaller circuit. And this is fine. You can do this. And you have like a variety of rewrite rules you can apply to this, and you have a variety of rewrite rules even more, and you have some even more rewrite rules, and even more rewrite rules, and you can go on and on and on and make it as complicated as you want. But here's a better idea. We can use this thing that we call the ZX calculus, which is a diagrammatic language for reasoning about quantum computations. Where, so it's called calculus because we can actually calculate directly with these diagrams. So you might be used to diagrams being a kind of like a visualization tool, but not like real mathematics. Like the real mathematics happens in equations. But this is like an actual diagrammatic calculus. So these actually represent concrete objects that you can transform with formal rewrite rules, and you can reason with these diagrams directly. And it turns out that these rewrite rules that I have here on the slide, these are complete for qubit quantum computation. So that means that if you give me two quantum circuits that implement the same operation on your quantum device, there is a sequence of these rewrite rules that will transform one into the other. Like I can always do this. It might just take a very long time. I might just have to apply very many rewrite rules to transform one into the other. Okay, so now I want to go through some of these rewrite rules and explain in a bit more detail how you can understand them and what they mean, and then give some examples of some properties about quantum computations you can prove with these. And then we're going to work towards like how you actually build software that exploits these rewrite rules and does some useful quantum circuit optimization. So here we have the same quantum circuit as before. So I'm just going to like demonstrate the high level, the idea here. So we are going to break apart these gates into smaller components. So it's going to look something like this. And then we have these local rewrite rules that we're going to apply. And they're all of this topological flavor where we're going to sort of combine things and cancel things and push things through each other until we end up with this really small thing. So in this case, this circuit ended up being quite trivial, and you get this completely disconnected quantum state. Okay, so let's see what's really going on here. So like, what are these diagrams actually? So in the same way as a quantum circuit is built out of quantum gates, these ZX diagrams are built out of things that we call spiders. We call them spiders because they look kind of like spiders with like these many legs coming in or out of these things. If you know what a tensor network is, this is a type of tensor network. If you don't know what a tensor network is, you can forget about that comment. But what these are is we have essentially two types of these linear maps that are defined in this particular way. So we see here in ket-Bra notation, this is just a sum of two of these ket-Bras. And we can think of this as saying the input state, either all the inputs are 0 and we output 0, or all the inputs are 1 and we output 1 and we get this additional phase attached to it. So it's like, if you know what the Dirac delta is, this is kind of like a big Dirac delta that forces all the indices to be the same. And then here we have the other spider. So we call the left one the Z spider, we call the right one the X spider. And this is the same thing within the different bases. So here we are testing things in the 0, 1 basis, and here we're testing things in this +1 basis. We call this a Z spider because this 0, 1 is also called the Z basis. We call this the X spider because this plus minus is also called the X basis. And so for instance, we can construct some familiar things using these spiders. So here I have a Z spider with 1 input and 1 output wire. And then by definition, it is equal to this thing with these cats and bras here. And then I can just see what matrices these are. And I see it's actually this matrix. And I take the sum. And then here I recognize this is actually my matrix of the Z phase gate. And I can do something similar with this X spider. And then this plus plus here corresponds to this matrix. This minus minus corresponds to this matrix. And this actually would correspond to an X phase gate if you kind of do some, if you do some trigonometry to this thing here. But the important thing is that the number of wires here is allowed to be any number. So we could have 0 inputs, for instance. We could have 2 inputs, 2 outputs, but we could also have 1 input, 2 outputs. So we could have any number of inputs, outputs on these spiders. So in particular, these are not unitary gates. So these are just some linear maps. Like they're not unitary. You can't necessarily execute these things directly on a quantum computer. They're just useful mathematical tools. So special notation, if this phase, this alpha, if this is 0, we just don't write it. So then we get this like smaller dot here, which is just equal to these things. And here we have some more examples. So for instance, if I take this X spider and I give it 0 inputs now and 1 output, then by definition, this thing here is just going to be equal to this plus plus minus. And then I can calculate this and I see it's actually equal to the 0 state up to the scalar factor square root of 2. And I can do similar calculations for these other things where if I put a pi phase on here, then instead of a plus here, we're going to get a minus. And that's because on the previous slide, we see that we get this e to the I alpha. And if I have e to the I pi, you get a minus sign. So that's why we have a minus sign here in the middle. The square root of 2 factors, they're usually not super relevant. So in this talk, I'm not going to write these. Like I'm just going to ignore these factors. I'm just going to say that this represents my computational basis states here on the left, or my plus minus states on the right here. Okay, so those are sort of my basic building blocks of ZX diagrams. And then what I can do with these is I can compose them together to create diagrams. And I can compose them in 2 different ways. I can compose them vertically. And if I do that, I get the tensor product of things. So for instance, here I've drawn a 1 input, 2 output spider, and it corresponds to this particular matrix. And I can here, for instance, take the tensor product with an identity matrix, and we just get this bigger matrix that I've drawn here on the right. And here's just another example where I have this 2 input, 1 output X spider, which corresponds to this matrix here. And then if I tensor it with an identity, I get this thing here. And then the other thing we can do is we can do a horizontal composition, which is just regular composition of linear maps. So in particular, here on the left side of this diagram, I have this diagram I showed before. It's a 1 to 2 Z spider with an identity. And here's on the right, there's like a identity with a 2 to 1 X spider. And if I compose them, I just get this composition of linear maps, and I can calculate what this is. And I get this map. And if you've done quantum computing for a while, this will look familiar. This is the actual C0 unitary matrix up to the scalar factor of 1 over square root of 2, which again, like we don't really care about. So we see that even though these building blocks we have, these Z spiders and X spiders are non-unitary, when we compose them together like this, we can build a unitary matrix, because the C0 thing is in fact unitary, and it is something that we can execute on quantum hardware. So we can use these small building blocks to build things that we can actually run on a quantum device. And so then how do we build arbitrary ZX diagrams? Well, we build them just by iterating these vertical and horizontal compositions. And then what's very nice about ZX diagrams is we have lots of symmetries to this. So this thing on the left is what I've shown you before. It's like we have this 1 input, 2 output Z spider, and this 2 inputs, 1 output X spider. And I can calculate this linear map, and I start with a C0 gate. And I can do the same thing with the map on the right, which now contains this 1 input, 2 output X spider and a 2 input, 1 output Z spider. And I can calculate that linear map. And it turns out that these 2 linear maps, they're exactly equal to each other. Now that seems like a coincidence, but it's really a fact that these objects, these spiders, they're defined in a very symmetric way in terms of the inputs and outputs. And what's very nice about this is that we can actually write this wire just horizontally. We don't really care whether this wire goes sort of from the top down or it goes from the bottom up here. In particular, we have these symmetries. That means that only the connectivity matters of these diagrams. So you can treat these diagrams as essentially as simple graphs, where undirected simple graphs, where we just write our diagram on the page and we can move these spiders around on the page, and however we write them, it will always represent exactly the same linear map. So in particular, for instance, we have here the spider on the left, which is a completely disconnected spider, and we can just move it around on the page wherever, and it doesn't matter. So to summarize what ZX diagrams are, we have these 2 generators, these Z spiders and X spiders. We can compose them horizontally and vertically, which corresponds to tensor product and just regular composition of linear maps. And then it actually doesn't matter like how we put our spiders on the page. We can just move them around, and it will always represent exactly the same linear map. So this is a pretty flexible language for representing linear maps. And then you can wonder, like, well, which linear maps can I write as ZX diagrams? And it turns out all of them. So ZX diagrams are universal. So that means that any linear map between qubits can be represented as a ZX diagram. So if I have any linear map from any number of qubits, so this could be 1 qubit, 2 qubits, like 100 qubits, to any other number of qubits, so this doesn't have to be the same number, then I can always find a diagram that represents it. This could be a really large diagram, like an exponentially large diagram. So the game is still like which linear maps have like nice diagrams representing them, which have small diagrams representing these linear maps. But it turns out lots of interesting linear maps have small ZX diagrams to represent them. Okay, so this is so far just notation for linear maps, right? But I said you can actually calculate with these diagrams. And so that brings me back to these rules. And I just want to go in a bit more detail on some of these rewrite rules and then use them in some examples. So I think one of these sort of more canonical rewrite rules, like a very familiar one, is what we call spider fusion. And this is essentially saying that if I have two spiders of the same type that are connected by one or more wires, I can just merge these spiders into a single spider where the connectivity to the outside stays the same and the phases just add together. So whenever I have two Z spiders, they fuse. Whenever I have two X spiders, they also fuse. This Z to X thing here is a C0 gate we've seen before. And then this thing here is a Z phase gate. In particular, this is a T gate. It's a 5/4 rotation Z basis. And what I can do here is I can fuse these top two things together using spider fusion. And then I can also unfuse it again in the spider direction, because all these rewrite rules, they go both directions. It doesn't matter in which order I apply them. So what's nice about this is I don't have to remember this particular rewrite rule that says, oh, a T gate commutes through the control of a C0 gate. I just remember that spiders of the same color fuse, and then I can just do this. Because here on the bottom, I have a different rewrite rule, which actually is a NOT gate or a Pauli X gate, which here I show that it commutes to the target of a C0 gate. And again, I might have to remember this rule specifically, like a X gate commutes through the target of a C0 gate. But here actually it's just like another example of this spider fusion. We're like, oh, these spiders of the same color, they just fuse. Yeah, and here in the bottom I have another example where I have two Z phase gates, where I have like this alpha rotation and the beta rotation, but actually these two Z phase gates, they just merge into a single Z phase rotation on my block sphere, and I can see this as another example of spider fusion. Another rewrite rule we have is the color change rule. And for this, I have this little special notation. So a Hadamard gate is extremely useful in quantum computing. It crops up everywhere. So we have some special notation for it. So we can write a Hadamard gate as just a sequence of spiders. You just have to trust me that like this sequence of ZX, Z rotation actually implements a Hadamard gate. But we introduced this notation of this little yellow box for this thing. And then we have these two rewrite rules. Well, first we know that the Hadamard gate is self-inverse. So if we do a Hadamard gate twice, it cancels. And the other special thing we know about a Hadamard gate is that it interchanges between the Z basis and the X basis. So it turns a 0 state into a plus state, and it turns a 1 state into a minus state. And so what that means for spiders is that if I take my Z spider and I surround it by Hadamard gates, it just color changes. It just changes into the other spider. And then I can combine these rewrite rules together to derive like slightly different rewrite rules. For instance, here on the left, I have my spider, which has some Hadamard gates just on the left. Then I can use this like Hadamard cancellation rule in reverse to introduce some pairs of Hadamards here on the right, which like, again, I'm allowed to use rewrite rules in both directions. So here I just replaced my identity wire with two Hadamards. And then I see I have my Z spiders fully surrounded with Hadamards. So then I can apply this other rewrite rule, and then I get this X spider here on the right. So I see what this essentially boils down to is I can push these Hadamards through my spider, and it changes the color of the spider. So this has a really like topological flavor, right? Like I have this graph, and then on this edge, like this is Hadamard, and I can slide this Hadamard along this edge, and if I push it through a spider, it appears on the other side, but then the color of the spider has changed. Yeah, and as a nice consequence of this, everything also holds with the colors reversed. Because if I've proven something with a certain coloring, with like Z and X spiders, then I can just push the Hadamards through it, and it flips all the colors from Z to X, and then it's also true. So like in the future, I'll be using some rewrite rules and sort of the opposite colors, because like it's also gonna hold. So as a small example, there is this state that's called a G8Z state. And again, this is a very common state in quantum computing. It's very useful. It's just this superposition of the all 0 state plus the all 1 state. Maybe you've seen it before in your previous talks. And then I claim that this following quantum circuit implements a G8Z state. Now, one thing you could do, like this is very small, so you could just calculate its matrix and or calculate the vector, and you would see, in fact, this is equal to a G8Z state. But if you get to like a much larger diagram, you don't want to do this because the matrix gets really large. But it turns out you can just prove this is correct in SELEX calculus. So as a first step, I just write this quantum circuit as a SELEX diagram. And so the way I do that is I just take each of these quantum gates and I just take its corresponding SELEX equivalent. So the Hadamard gate, it becomes this yellow box that we discussed before. And each of these C0 gates, it becomes precisely this Z spider connected to an X spider. And then these 0 states, they become this like X spider here that, yeah, I've also showed that like, if you have this 0 input, 1 output X spider, it's like up to the scalar factor square root of 2, it is just a 0 state. So we can in fact represent this state, this circuit diagram, by this particular SELEX diagram. And then we can start to simplify this diagram. So you see, for instance, here that I have an X spider, which is connected to an X spider. And here in the bottom I have an X spider, which is also connected to an X spider. So I can apply spider fusion to it. And these spiders just fuse together. And then I have fewer spiders in my diagram, which the diagram is now smaller. Then what I can do additionally is now I have these two Z spiders here. They're also connected together, so I can apply spider fusion to them. And then here is something that we haven't discussed really yet, but I have here a spider with a single input, single output, and it has a phase of 0. And just this turns out to just be identity. It doesn't do anything, so I can just remove it. So if I do that, I do spider fusion and remove these things, I end up with this thing. Now, finally, I have this Hadamard gate. And I told you this rule that like if a spider is fully surrounded by Hadamard gates, I can absorb the Hadamars and it changes the color. And here I see an X spider, which is fully surrounded by Hadamard gates, right? In this case, there's only a single wire, but it's fully surrounded. So I can just absorb the Hadamard and it changes the color. And then again, I have two spiders of the same color, so I can just merge them. And I'm left with this thing, which is a single spider. And if I sort of go back to the definition of my Z spider, I see that by definition, this thing is exactly equal to this thing here. So I've verified now that this quantum circuit actually implements this state that I said it would. By the way, if there's like questions about the stuff that I talked about, feel free to ask. So another slightly more complicated example. So I'm not sure you've seen the quantum teleportation circuit before, but quantum teleportation is a protocol where we have these two different parties. We have Alice and Bob, and like maybe Alice and Bob are very far apart. But before they went very far apart, they shared an entangled quantum state. So that's like written by this psi that they both share. So they share this thing that we call a Bell state. And then what quantum teleportation allows us to do is that Alice could put in some quantum state on the top wire here. And then she does a particular unitary operation. And then she measures both the state that she has and she measures her part of the Bell state. And then she sends the classical outcomes of these measurements to Bob. So she just doesn't send any quantum information. She just sends classical information to Bob. And then Bob does a certain quantum correction to his state. And then the claim is that whatever state Alice had at the start, Bob now has that state. So Alice has transmitted her quantum state to Bob just by transmitting some classical information. And again, we can prove this we can prove that this is correct, but this quantum circuit actually does this in ZX using and so the way we do that, again, as a first step, we need to write this quantum circuit as a ZX diagram. And now there's been a bit more complications. So first of all, this shared entangled state that Alice and Bob have. It turns out that in ZX, we can just write this as this what we call a cup. So it's like a wire that just goes from Alice to Bob, and it literally shows it's like entangled, right? It sort of goes across this line from Alice to Bob. And then the other new thing is that we have these measurements. So what a measurement is you get either the 0 outcome or you get the 1 outcome. And you don't know beforehand which one you're going to get. But you're going to get like a 0 outcome or a 1 outcome. And so the way I represent this in ZX is I have this Boolean variable a. So a is going to be either 0 or 1. And if a is 0, that means I got the cat 0 outcome. And if a is 1, that means I got the cat 1 outcome. And the same thing here with this qubit here. So this just represents a measurement and the fact that I have some at this point in the measurement outcome, I know what A and B is because I've measured it and some classical information. And then Bob just needs to use the classical information to do something. So I see here, for instance, this first outcome, I see this first outcome goes here, it does an X correction. And here, see this A pi is also used here to do an X correction. And this thing here is used to do a Z correction. And you see, in fact, it's used to do a Z correction. Yeah, I notice I haven't given the full details, but I guess just trust me that this is, in fact, a faithful rendition of what quantum teleportation does. And then again, we can simplify this diagram and show this in fact correct. So again, we have these spiders that are of the same color, so we can fuse them together. Again, we have a Hadamard that fully surrounds an X spider, so we can color change. We have these two spiders of the same color, so we can fuse them. And now we can use this fact that, again, we don't really care how wires are on the page. We can move things around on the page, and it represents the same linear map. So I'm just allowed to make this Bell state in just a regular wire. And then I'm just gonna, again, fuse spiders of the same color. And then here I have this thing 2b pi, and I can check that if b is 0, I just have a 0 phase, which becomes identity, and I can remove it. And if b is 1, I have a 2 pi phase, and like a 2 pi phase is a full rotation, which again is an identity, so I can remove it, and it goes away. I do the same thing with this thing, and remove it. And then I end up with just a line that goes from Alice to Bob, which I can literally see that whatever Alice puts in this wire, it's going to end up at Bob's side, right? So this is just a visual representation that this information indeed flows from Alice to Bob. Okay, so then some more rewrite rules, and then I'm going to also get some more examples at the end. So we have this other rewrite rule, which says that if I have a pi phase, which is like a Pauli X gate in this gate, I can, again, like with the Hadamard, I can push it through the spider, and it appears on all the other wires. But now instead of color changing the spider, it's just going to get me a minus face. So again, you could write out the linear maps they represent. You can kind of see that this should be correct. And the other thing we have is that we have this spider here with 0 inputs and 1 output, which we know is the cat 0 state. And then if you kind of look at the definition of a Z spider, we can kind of see that if we plug in a 0 state, we should get out the all 0 state. So then we see that if we sort of put the 0 state in here, then the spider disappears and we get this completely disconnected set of spiders. So it kind of allows us to blow up a spider and it sort of goes through the end there. Yeah, and so like one way to remember this is that these pi phases and states, they actually copy through the other color spider. And again, we can combine some rewrite rules to then do it with some other states. So here, for instance, I have the state with a pi phase, which actually represents a cat1 state. And then I could unfuse this pi phase. So I use my spider fusion rule in the opposite direction to get my pi phase onto its own wire. And then I push it through this spider. Then I apply this rule on the right to get rid of the spider. And then I fuse these things again. And then I see that actually I've now taken this pi phase and I've copied it through and it appears on the other end here. Yeah, so this brings me to the most complicated rewrite rule. And to understand this, we have to understand a little bit about a way we can understand these Z spiders and X spiders, which is that if we now write, so here we have the case where there's a phase of 0, and here we have there's a case of pi. But we see the outcome is kind of the same thing. Like here we get all zeros, here we get all pi's. So we can kind of parameterize this rewrite rule and say, if A is 0, this rewrite rule works. If A is 1, this rewrite rule works. So this kind of works for both cases. And then the way we can see the Z spider, what it does is it copies this variable A to all the outputs. So we plug in this A pi and we get A pi at the end. So Z spider acts like a copy map. It copies the computational basis state. And then for X spiders, we can do this thing and we can fuse these spiders and we can kind of see that what this does is it takes an XOR of these two variables A and B. So in the same way, we can kind of see that an X spider acts like an XOR map. So it's if I plug in 0, 0, I get 0. If I plug in 0, 1, I get 1. And if I plug in 1, 1, I also get 0 because I have a pi phase plus a pi phase, which equals a 2 pi phase, which is just equal to 0. And one thing that we classically have is that if I XOR two variables, and then I copy the outcome. So now I have here two XORs of the same variables. Then another way I could have done that is I could have copied my inputs first and then just calculate the XOR twice of those same inputs. So you can kind of trace the computational paths here, and you can just see that classically these two things should be the same thing. That what you calculate on the left is the same thing as you calculate on the right. And so what you can do is you can translate this classical equation into a ZX equation, and it will look something like this, where I have like an X spider on the left and a Z spider on the right. And I can interchange these two things, where now we have Z spiders on the left and X spiders on the right. And they get connected in this sort of like fully connected bipartite manner. And this is the most complicated rewrite rule. This takes quite a while to get used to. And then one thing we can prove with this is this well-known fact that if you have like 3 CNOT gates in a row, then you can make a swap gate out of it. So for instance, here I have these 3 CNOT gates. So here I have a CNOT gate with a control on the top and a target on the bottom. And then I've swapped them to, and then I have the same thing. And again, I claim this indeed implements a swap gate. I'm going to go through this a bit quickly because I want to show it in like a different way a bit later. But one thing we can do is we can kind of deform this diagram, because again, it doesn't really matter. Like we can drag stuff around in the plane and it's the same diagram. So here we can have to trust me. This is the same diagram. I just move some wires around. And then we see that we have this location where we can exactly apply the bioalgebra rule. We can exactly apply this rule that we just saw. So I apply it there and I get this thing. And then I deform it again and I get this thing. And then I can spider fuse because I have these two Z spiders connected to each other, I have X spiders connected to each other. I can fuse them, I get this thing. Then it turns out there's this other weird rule, which I'm not going to say too much about, but yeah, if a Z spider is connected twice to an X spider, it turns out that the wires just fall off. So I can just do that here and the wires disconnect. And then these are just identities and I'm just left with a swap gate. Now, so one thing I want to do, again, I said I was going through this a bit quickly. So one thing I want to do here is I want to show you a bit of software that we developed. So this is a graphical user interface for working with ZX diagrams. It's called ZX Live. You can just go to GitHub and download this. I'm just going to input a circuit here. So I'm just going to like write here. So this is this chasm format. It's like a way to write some basic quantum circuits. So here I'm just going to write that I have these 3 CNOT gates in a row, where they act from the first qubit to the second qubit, and then the second qubit to the first qubit, and the first qubit to the second qubit. And I'm going to say, okay, I don't want this third qubit. I'll delete that. And then here I have my ZX diagram. I'm just going to like make it a bit larger. just so that I have a bit more space to work with. So this is a ZX diagram, and then I'm going to start a derivation. So I'm going to start a proof with this thing. And then I set like this deformation I did, right? So now I can just do this deformation. I can just move things around here on the plane. So I can bend some wires, sorry, like this. So I see here that I have, in fact, this bialgebra thing I said I had here. Then I have my rewrite rules that I can apply. So I have here this rewrite rule that is strong complementarity in opposite direction. So I apply this, these things get applied, and I just deform it again over here, like so. Now I wanna fuse these spiders, and I can just do that by dragging them on top of each other. So I do this fuse, I can do the same thing here. Now see I have these two wires here. Now it turns out we built this nice thing that we call the magic wand. So here's like a magic wand with lots of sparkles. And then I see I have these two wires, and I know I can get rid of them. So I just drag my magic wand across them, and they disappear. And I know this is an identity, so I can just drag my magic wand across the identity to remove it, and here as well. And then I see I get these, I just get a swap. So I indeed have the swap thing. I can step through my proof and see that indeed I have built my swap. Yeah, so maybe you find that too much effort. Luckily, we have all these automated ways to do stuff. So I could have also just selected the whole diagram, and then I go to my simplification routine and I say, just go and reduce this for me as much as possible. And it also just makes it into a swap like this. Okay. So that's like a whole lot of examples and some more details on these rewrite rules. But yeah, that's the ZX calculus in a nutshell. And it turns out it's pretty useful. So an important question here is like, how do we scale up, right? Because the things I've shown you, there are essentially some toy examples, some nice examples that demonstrate some useful identities. But like, how do you go to really large scale things? And the answer is like, you do some software automation. So we built this library that we call physics. So PyZX, but we just pronounce it as physics, like physics without the H. And this is an open source library where you can deal with large scale diagrams. And there's a lot of visualization tools. There's a lot of implemented rewrite rules, circuit optimization things. But it's written in Python, so it's maybe not the fastest thing. So if you really need speed, we also have this thing called QuSix, which is QuickZX, which is written in Rust. And we built this thing specifically to do classical simulation with ZX calculus, which maybe I'll get to classical simulation. And then there's this thing that I just showed you, ZX Live, which is built on top of physics. And it allows you to sort of more interactively work with diagrams and do rewrites and proof stuff. So how do we do automated rewriting? So the main idea is we want to turn these bidirectional rewrites that go both directions, and we want to turn them into directed rewrites. So spider fusion is a thing that can go both directions, as we've seen. But for automation, you want to say, oh, I'm going to only apply this in one direction. For instance, here, from going from 2 spiders to 1 spider, like there's like a very clear metric that I'm decreasing the number of spiders. So I'm going to only apply this rewrite rule in a direction where I decrease spiders. And then what you can do, if you do this with all these rewrite rules, you find some nice directional rewrite rules, then you can find efficient rewriting strategies for certain tractable fragments of ZX calculus. So I'm not sure if you've seen like Clifford's quantum computation or a stabilizer quantum computation. It turns out this also very nicely corresponds to things in ZX calculus, and you can also do efficient rewriting on these types of diagrams. So for instance, we have this library, this set of rewrite rules where I don't think I'm going to say too much about this. The important things here are these are directed rewrite rules, and they very clearly reduce some metric. So these spider fusion rules, they reduce the number of spiders because they just fuse things. These identity removal rules, they just also remove spiders. And this color change rule, it just turns X spiders into Z spiders. So it always reduces the number of X spiders that you have. Yeah, and this blue dotted line, this is just a shorthand for a Hadamard. So whenever you see a blue dotted line, it just means there's a Hadamard on this edge, because otherwise these diagrams, they get really cluttered. And then I have these two special rewrite rules that look very complicated. We don't have to remember the details. The important part is on the left-hand side of these rewrite rules, there are more spiders than on the right-hand side on both these cases. So you can just keep applying these rewrite rules and you will always remove spiders. And it will always terminate at some point, because at some point these rewrite rules don't match anymore. And that means there are no more spiders to remove with these rewrite rules, and you're done with the rewriting. And so then what do we do for circuit optimization? So there's 2 phases to this. So the first phase is just simplify your diagram. So you have written your quantum circuit as a ZX diagram. So here I have a big quantum circuit. And then you just keep applying your rewrite rules until they don't apply anymore. And then for instance, you get some diagram like here on the bottom, where like we see like obviously it's much smaller. Right, it has way fewer spiders. We have some like formal statements about which spiders you can remove and which ones you cannot remove. But what we also see is that it doesn't look like a quantum circuit anymore. Like it looks like some arbitrary diagram. And so that brings us to the second stage, which is that we have to turn this arbitrary diagram into something that actually looks like a quantum circuit, because we know how to execute a quantum circuit on a quantum device, but we don't know how to execute a ZX diagram on a quantum device. So the thing we do is this process that we call circuit extraction. So we extract a circuit from a ZX diagram. And the way we do that is we're going to start at the end of the diagram. So we're going to start on the right-hand side, and we're going to kind of absorb gates one by one into like a circle-like format. So at the start, this is very easy. We see we have these blue dotted lines. And again, this is just shorthand for that there's a Hadamard on this wire. So we just have these Hadamard gates, which are like unitary gates. We can implement them on quantum hardware. We're happy. Then we get to this next layer, which are spiders, which do not correspond to gates. So we have to do something. And the first thing we do is we just extract these phases onto their own layer, because these phases, they do correspond to unitary gates. And so now, like, we're done with everything on the right of this block, but we have this layer of spiders that we call the frontier. And on this frontier, we have to do some rewriting to make it look like a quantum circuit. And so what we see in particular is, like, here we're actually happy because there's a single connection to the left, and a single connection we know how to deal with. So these things with a red mark is actually like, oh, we know what to do. We know we need to bring these spiders to the right-hand side. So we kind of like, we just take them immediately to the right and we extract them out into something that looks more like a circuit. And then we're at this point, and then, yeah, we again have these phases on these spiders, and we put the phases there. Yeah, and then we're kind of stuck. And then we see this thing where, like, oh, I have this spider here, but it kind of has this connectivity going to this other side. And now I have to do some special rewriting. And it turns out that what you can do to deal with this thing is, it turns out you can just extract a C0 gate from this. So you can just turn this connection into a C0 gate, and you just do that, and then you can make some more progress and just keep doing this until the whole diagram is extracted. Like, I realized I went through this a bit quickly. The details are a little bit technical. It involves a lot of Gaussian elimination, or like Gauss-Jordan reduction of matrices. But the important part is we can do this, and it's efficient. So you can transform your your ZX diagram back into a quantum circuit. Yeah, and then you get a quantum circuit. So I talked about optimization, but like, what are we actually optimizing? And so it turns out that there's like different metrics that we might care about in quantum circuit optimization. So near term, the most important thing we could try to optimize is the number of entangling gates. So that, for instance, the number of C0 gates we have. And this is because entangling gates are usually more noisy, because currently the main bottleneck we have for quantum computations on physical hardware is that every single gate is noisy. And at some point, we've done so many gates that the noise starts to dominate, and that we're losing the data that we have in a computation. And the C0 gates are like an order of magnitude more noisy than single qubit gates. So we want to especially minimize the number of entangling gates. But if we get the long term, when we are thinking about error-corrected quantum computations, and again, I'm going to not say too much about that, then this metric of what we care about changes. Because it turns out that if you're working in error-corrected quantum computation, which gates are hard changes a lot. And in particular, all the Clifford computations become much cheaper, and the non-Clifford computations become expensive. And in particular, there's just T-gates. If you don't know what the T-gate is, then don't worry too much about this. There's a different metric that we care about for optimizing. And so it turns out for 2-qubit gate count optimization, if you're a bit smart about which ZX rewrite rules you apply, and if you're smart about how you extract a circuit from the diagram, it turns out you can make some methods that outperform other circuit-based methods on 2-qubit gate count. So this like near-term metric that we care about on certain circuits where, on other circuits, they seem to be already quite optimal, so there's not much we can do. But then other circuits, we can actually we can do a bit more. And then this other metric, this T-count reduction, there it turns out it also works really well. We essentially do all the rewrites we can. We try to reduce the T-count as much as possible. And we have this paper from last year where we show that if you define it in a bit of a technical way, but this kind of gets you an optimal number of T-gates. If you define the word optimal very carefully, then this is like optimal in a certain sense. Okay, let me see at the time. Okay, so I've been talking for a while. I can start talking about a different topic. I guess I want to kind of check with the organizers if there's maybe lots of questions, and if I maybe should stop here, or if I should keep going for a little while longer.
Hi, yeah, so we have some questions, not a huge amount. The people that are after you do need to stay on time, though. So, we're ending your session at I'm at 10 o'clock Central Time, so I don't know what time that would be for you. So we do have some questions. Yeah, so if you want to take more time and talk, or if you want to do questions, which one is it that you wanted to do?
I'm just going to quickly go through this, I think. Yeah. So I think the main point I want to get across with this is that T count is the number of T gates in your circuit. It is important for like these large-scale fault-tolerant quantum computations, but we're not there yet, right? We don't have these quantum computers today. So you can also get like, why would you care about this today? And then it turns out that the T count, number of T gates, is also an important metric for how hard it is to simulate a quantum computation on a classical computer. So if I have some big quantum computation, the naive way to simulate it would be to take my whole state, my exponentially large state, and just put it in memory and just update it over and over again and just calculate the state directly. But this takes exponential space in the number of qubits. So this like times out at a certain point. But it turns out you can do this method, which actually is exponential in the T count instead of the qubit count. So you could have a very large computation, very many qubits, very many gates. And as long as the number of non-peripheral gates is small, you can still efficiently classically simulate it. And so there are these different metrics of hardness of simulation. So I talked about number of qubits. Another metric you might have seen is tree width. This actually is related to like tensor networks and how hard it is to contract a tensor network. But then there's also this T count. I think I won't say too much about this, just that it turns out that with SELECT diagram and this optimization strategy, you can get a pretty efficient classical simulation library that is very beneficial when the T count of the circuit is quite low. I'm just going to skip all of this. And so then in summary, I introduced the SELECT calculus, which can represent any linear map that you might care about, so any quantum computation you might care about. And then I've shown some rewrite rules on how we can use these to prove some nice properties about quantum computations. And then I've given this like more of a sketch of then how you can use this to actually optimize quantum circuits. And then also very briefly that, you can also use this to actually simulate quantum computations as well. And there's a whole lot more stuff you can do with SELECT diagrams, like thinking about error correction or fault tolerance or designing protocols. And if you want to learn more about this, we've written a book. So you can just check it out. It's available for free at this GitHub link. So you can just go there. And if you want to learn more about SELECT calculus, we have this website where there's also a list of essentially all the papers that do anything with SELECT calculus. So you can like maybe go through there and find some things that you find interesting. And if you want to learn a lot more about quantum computing, we in Amsterdam have this quantum computer science master, which you can register for. I think registrations for next year are not yet open. They open in October, but you can already think about it. And thanks very much for listening.
All right, thank you very much. So now we can do some questions. Let's start out. We have somebody asking a simple question. Why were the measurement symbols pink in your presentation?
Like why pink and not green?
Did it have any significance for them to be pink, or is that just the color you picked?
No, so when we write a measurement symbol like this, we usually mean we measure in the computational basis. So we're measuring, is this state cat0 or is this state cat1? And in the SELECT calculus, whether something is cat0 or cat1, that's exactly represented by a red spider. If we were to have done an X basis measurement, so is the state plus or minus, then we would have written a green measurement. So in particular, when I do this proof, right, at some point I change the color of this thing to this thing. So I have a Hadamard and then a computational basis measurement. I could have just written this as a measurement in the X basis together, but I figured I'd just stick to the standard notation of having a regular measurement like this.
Thank you. All right. Somebody is asking if you could provide learning resources for ZX calculus to strengthen fundamentals and to practice. If you have those and you want to share them with me, you can email them with your presentation and we can post them in the LMS.
I would say go look at the book. There's 600 pages of learning materials and over 100 exercises. So I would say that's plenty of material to start learning. If you want something that's like a little bit shorter than that, then you could also go to, let's find it. So I've written this paper, which is more of a review for like professionals working in quantum computing. But this also, it's essentially a more elaborate version of the talk I've just given, and it explains all the things I've just did in like more detail. Like it has like recognizable things, although it is in black and white instead of color. But
awesome. All right, next question. When simplifying / absorbing spiders / gates, does that change the value of the final spider?
I'm not sure exactly if I understand the question. These rewrite rules preserve the linear map that the diagram is implementing. So if you apply, let me go back to the actual rewrite rules. So here I have these rewrite rules. What's special about these rewrite rules is that if you give me some diagram, this diagram implements some linear map. And then if I apply one of these local rewrite rules, I get a new diagram, but this diagram is promised to then still implement the same linear map. So it doesn't change the linear map you're implementing. This is why we could treat these examples as actual proofs, right? Like I start with this thing, which implements the quantum circuit. And then at the end, I've reduced it to this thing. And I claim this is still the linear map that the original thing was. So it is in fact like still representing the same thing, just with a different diagram.
Sorry, I was muted. When representing circuits, we usually use gates as intermediate representation. What restricts us from using ZX spiders as a way to write down circuits if it helps to rewrite them more compactly?
So this is essentially the circuit extraction problem. So if I give you like a diagram like here on the bottom, like how would you implement this on a quantum computer, right? Like you would somehow have to find like this thing here in the middle, which has like two wires coming in, three wires coming out. Like what does that mean for a quantum computer? And you could say like what it means is like, well, I extract a circuit from it, and that tells me how to implement it. You could do something that's called measurement-based quantum computing, where you essentially prepare this whole diagram as like a big graph state, and then you apply these phases to them, and you measure out these things, and then based on the measurement outcomes, you feed forward some corrections. And it turns out there's a very, very strong connection between ZX diagrams and measurement-based computations. So if you say like, oh, I want to execute my ZX diagrams as like directly as possible, you should use some kind of measurement-based system. And this is quite natural for something like photonics. So there's quite a few photonics companies, and they are using ZX diagrams directly to represent resource states for their photonic cluster states and stuff.
All right, thank you. How do modern quantum compilers use ZX calculus to optimize quantum circuits, and how do they verify that the optimized circuit is mathematically equivalent to the original one?
Yeah, so currently we have our library, physics, which does this, and then also QuSoft. No other library directly uses physics. Like there's papers that like use our library to optimize stuff. Yeah, like since we do quite a destructive thing to the circuit, right? Like we compress it down to a small diagram, we extract a new circuit. This can give you a smaller circuit, but it could also give you a bigger circuit. So it's kind of like you have to sort of try per circuit whether it's actually beneficial to do this very rigorous re-synthesis of your circuit. And in terms of how do you verify it's correct? So we do this in physics by, so if you give me if you have your original circuit and you do this whole protocol and you get some optimized circuit at the end, then one thing you can do is you can take this optimized circuit and you take its adjoint, so its inverse, and you compose the adjoint with your original circuit. And now you have a circuit that's mathematically should be equal to identity. And then you again apply ZX rewrites to this circuit, and you see if it in fact reduces to the identity circuit, so where there's no gates left at all. And if you can successfully reduce to identity circuit, then one of two things have happened. Like either you did all your rewrites correctly, and so indeed the optimized circuit you had was indeed the correct optimized circuit. It was mathematically equal to the original circuit, or somehow an error has crept in producing your optimized circuit. And then that exact same error canceled out in this other rewrite sequence, even though you did a completely different rewrite sequence. So it's very unlikely that happened. So we've used this to debug our methods, and we've also used it to debug other methods, and then also found bugs in other people's methods. And so far, this seems to have worked quite well. And like people haven't found any bugs in our unitary optimization thing. People have found bugs in our non-unitary things, but this is mostly to do with scalar factors, where like we've been a little bit less careful, and like we're slowly fixing all these bugs.
Okay. Actually, building off of that, how does ZX calculus help with quantum error correction?
That's a very complicated story that I cannot really explain in a couple of minutes. One thing it's very useful for is that the regular quantum circuit notation really likes things to be unitary. And when things involve measurements, it becomes kind of awkward to work with. And so ZX calculus is by its nature more free than just representing unitary things. Like it represents measurements very natively. And the quantum error correction is all about doing smart measurements and doing corrections based on that. So in this sense, you can just much more directly represent a quantum error correction protocol in ZX than with like a regular circuit notation. Another thing it's very useful for is the surface code is one of the most well-studied quantum error correction protocols. And the native entangling operation on the surface code is not like a C0 gate or a CZ gate or any unitary operation. The native operation on surface code is something called lattice surgery, where we are merging patches and we are splitting patches. So it's a non-unitary operation. And these non-unitary operations turn out to correspond exactly to Z and X spiders. So if you're representing a computation, like a logical computation on a surface code, it directly corresponds to a ZX diagram. It does not correspond to a circuit-like notation. So people are using it for like compiling surface code logical computations. Yeah, and then very recently, something I've been involved with is we have this stronger notion of equivalence between ZX diagrams that we call fault equivalence, where two diagrams have the same fault tolerance properties. And then it turns out you can rewrite diagrams while preserving fault tolerance. And then in this way, you can construct quantum circuits that are by their very nature fault tolerant. And this is like a very useful thing to do. And this is pretty new, and we're currently just exploring what we can use this for.
All right, there are more questions, but we do have to move on to our next session. So I'm going to thank everybody for their questions. Thank you again, Dr. Van de Wetering, for joining us today. We appreciate your sharing your knowledge with us. And again, if you have slides and things that you want to share with the participants, you can email those to me and I'll post them in our LMS for us to have access to. So we're going to have a few seconds to shift. Again, thank you, Dr. Van de Wetering.
Thank you very much.
Thank you so much.